Have you ever stopped to think about how scientists actually work with stuff that's way too small to see, let alone count? I mean, atoms, molecules, they're invisible. Well, today we're pulling back the curtain on one of the most clever tricks in all of chemistry. It's a concept that lets us count particles by the trillions, just by weighing them. Welcome to our explainer on the mole.
So here's our game plan. We're going to build this idea from the ground up. First, we'll get straight on the difference between atoms and molecules. Then, we'll figure out how on earth you can weigh something so tiny. That'll lead us to this idea of a special counting number, kind of like a chemist's dozen. And that, my friends, brings us to the star of our show, the mole. Finally, we'll see how this thing is actually used. Let's do this. All right, first things first. We need to know who our key players are. In the world of chemistry, everything, and I mean everything, starts with atoms and molecules. They sound pretty similar, but they play totally different roles in the story. This chart lays it all out pretty clearly. The easiest way to think about it is like this. An atom is a single Lego brick. It's the smallest possible piece of an element, like hydrogen or carbon. Molecules? Well, that's what you get when you start clicking those Lego bricks together. They're basically teams of atoms, all held together by chemical bonds. And that's why individual atoms are super reactive. They're always looking for another atom to connect with. Molecules, on the other hand, are way more stable and just hang out on their own. Okay, so we've got these tiny little particles. But in a real lab, you can't just pick one up and plop it on a scale. They are unbelievably, ridiculously small. This was a huge headache for chemists for a long time. How do you measure something you literally can't see or weigh? I mean, seriously, think about that. It's like trying to weigh a single speck of dust on your bathroom scale. It's just not going to work, right? So chemists had to get really, really creative. They had to invent a whole new system based on comparing things instead of measuring them directly. And here is that brilliant solution: relative molecular mass. The idea is, instead of asking, how much does this molecule actually weigh in grams, we ask, how much heavier is this molecule compared to a standard? And that standard is the carbon-12 atom. It's a genius workaround, and because it's just a comparison, a ratio, it doesn't even have units like grams or kilograms. Let's see it in action. Say we want the relative mass of sulfuric acid, which has the formula H2SO4. It's basically like following a recipe. First, you just list your ingredients. We've got 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. Then, you look up their individual relative atomic masses. And finally, you just do the math and add it all out. And there you go. The relative molecular mass is 98. Now, what does that number actually mean? It tells us that one single molecule of sulfuric acid is 98 times heavier than 1/12 of our standard carbon-12 atom. It's a super clean, simple way to compare how heavy different molecules are. Okay, great. So now we can figure out the relative mass of a single molecule. That's a big step. But here's the reality check. Chemists never work with just one molecule at a time. They work with, well, a lot more. And when I say a lot, I mean numbers that are just mind-bendingly huge. In the tiniest drop of water, there are more molecules than you could possibly count in a lifetime. So this problem of scale is a big deal. We need a way to talk about these massive quantities without our heads exploding. You know, we already do this in everyday life. We don't say, I'd like to buy 12 donuts. We say, I'll take a dozen donuts. We group things into convenient little packages like a pair for 2 things or a dozen for 12. Well, chemists needed their own special version of a dozen. Just, a dozen that was built for absolutely astronomical numbers. And that thinking brings us right to the heart of today's explainer. We're about to meet the ultimate solution for counting the uncountable. It's called the mole. And yep, it's spelled M-O-L-E. Just like a dozen always means 12, a mole always means a very specific and very, very large number of particles. It's the official unit chemists use to count their atoms and molecules. And here is where it all clicks together. Remember our standard, the carbon-12 atom? Well, a mole is officially defined as the number of atoms you'd find in exactly 12 grams of carbon-12. This is the master stroke. It creates a perfect bridge between the relative mass we talked about and a real-world measurable mass in grams. So, what is that magic number? There it is. 6.023 times 10 to the power of 23. That's a 6 followed by 23 zeros. It's a number so huge, it's almost impossible to really wrap your head around. That is the chemist's dozen. This gigantic number has a special name, Avogadro's number. And the beautiful thing is, It's universal. 1 mole of water has this many molecules. 1 mole of iron has this many atoms. 1 mole of anything at all contains this exact number of particles. It's our go-to counting number for everything in chemistry. Okay, so what's the big deal? Why go to all this trouble to define a ridiculously huge number? Well, this is where the magic really happens. The mole lets us build a bridge between the invisible world of single atoms and the very visible, measurable world of the lab. And here it is, the big payoff. Remember that unitless number, the relative molecular mass? The mole connects it right to our lab scales. Let's go back to our sulfuric acid example, which had a relative mass of 98. Well, gram molecular mass tells us that if you weigh out exactly 98 times grams of sulfuric acid, you will have exactly 1 mole of it. You'll have 6.023 times 10 to the 23 molecules right there on your scale. We can finally count invisible particles just by weighing them. How cool is that? This opens up a whole new toolkit for chemists. The mole becomes the central hub connecting everything. If you know the mass of something, you can find the moles. If you have a certain number of atoms, you can find the moles. It lets us translate between mass, moles, and the number of actual particles. And the mole's power doesn't stop at mass. It's also incredibly handy for working with gases. It turns out that 1 mole of any gas, doesn't matter if it's helium or oxygen or whatever, will always take up the same amount of space under standard conditions, 22.4 liters. This is a fantastic shortcut that makes calculations with gases so much easier. So what's the big takeaway here? The mole isn't just some abstract giant number. It's the essential bridge that connects the tiny, invisible world of atoms to the real, tangible world we work in. Which brings me to one last thought. A normal glass of water is about 250 grams. That works out to be almost 14 moles of H2O. So the next time you take a sip of water, just think about it. You're not just holding water, you're holding 14 of the biggest dozens in the entire universe.